Today we will be talking about power series and finding the radius and interval of convergence. Let's say we have the series of n times x plus 2 to the power of n divided by 3 to the power of n plus 1. We know this is a power series because we have powers of x. To solve a power series, we use the ratio test, where we take the limit of n as it approaches infinity, we sub n plus 1 for every n in the series, and then divided it by the original series inside absolute value brackets. So in this case, we will write limit as n approaches infinity, then absolute value brackets, n plus 1 times x plus 2 to the power of n plus 1 divided by 3 to the power of n plus 1 plus 1. Then we divided it by our original series. When we divided two rational expressions, we use the keep change flip trick, where we keep the first expression, change from division to multiplication, and flip the second expression. Now we use some basic exponent laws to break up the expression so we can cancel some values. According to the exponent law, if two variables with the same base are being multiplied, then their exponents can be added up. So if we have x plus 2 to the power of n plus 1, then it equals to x plus 2 to the power n times x plus 2 to the power 1. We will also apply this rule to 3 to the power of n plus 1, which becomes 3 to the n plus 3 to the 1. Now we cancel the 3 to the n, 3 to the 1, and x plus 2 to the n. Now we write our limit after it's been simplified. We do not need the absolute value bars since the expression is positive. Now to evaluate the limit for n plus 1 over 3n, we will divide the top and bottom by n to the highest power in the denominator, which is 1, so it's just n. We will get limit as n approaches infinity, n over n plus 1 over n divided by 3n over n. Now 1 over n as n approaches infinity is just 0 since it's 1 over a very big number, which just ends up being a very small decimal number. N over n is 1, and 3n over n is 3. So after we simplify, we will get 1 over 3 times the absolute value of x plus 2. Now we set 1 over 3 times the absolute value of x plus 2 less than 1, and we multiply by 3 on each side, which gives us the absolute value of x plus 2 is less than 3, and 3 is our radius of convergence, regardless of what x is being added to or subtracted to in between the brackets, as long as there is no coefficient beside the x. Now our interval of convergence will be x plus 2 is less than 3 but greater than negative 3, and we got this number from our radius of convergence, except it's positive on the right side and negative on the left side. We isolate for x by subtracting 2 from all sides, and we get x is greater than negative 5 and less than 1. Now the last step is check our endpoints. This means we will check if x is convergent at negative 5 and 1. If they are, then we will add a greater than or equal to sign or a less than or equal to sign as opposed to just greater than or less than. To check endpoints, we sub each endpoint into the series. So when x is equal to negative 5, the series becomes n times negative 3 to the power of n over 3 to the power of n plus 1. And using exponent laws, which states that if two variables have the same exponent, then we can multiply them. But in this case, we will break negative 3 to the power of n to negative 1 to the n times 3 to the n. This way we can cancel 3 to the power of n, and we evaluate the limit as n approaches infinity for n times negative 1 to the power of n divided by 3. And as n grows larger, we will have a very huge number over 3, which does not approach a finite value, but approaches infinity, so it's divergent, which means the series does not converge at x equals negative 5. Now let's check the other endpoint. When x is equal to 1, the series become n times 3 to the n over 3 to the n times 3. 3 to the n cancels, and we are left with the limit as n approaches infinity for n over 3, which again, will grow non-stop without reaching a finite number. So divergent at x is equal to 1. So therefore, the radius of convergence is 3, and the interval of convergence is x is greater than negative 5, but less than 1, or you can also write it as negative 5 to 1 using the circle brackets that indicate that the endpoints are not included. Let's look at another example. Let's say we have the series negative 1 to the k times 3 to the k times x to the k over k factorial. Let's start by applying the ratio test. So limit as k approaches infinity, then absolute value brackets. Then we will sub k plus 1 for every k value in the first expression, then multiply it by the reciprocal of the original series. Now we will break up the expression into smaller parts in order to be able to simplify it. Keep in mind that k plus 1 factorial is equal to k plus 1 times k factorial. And then we break up the exponents with the same base. And we can cancel negative 1 to the n, 3 to the k, x to the k, and k factorial. We will write out what are left with, which is the limit as k approaches infinity for 3 divided by k plus 1 times the absolute value of x. Now divide the top and bottom by k, and we will get 3 over k divided by k over k plus 1 over k. Now in the numerator, we know that as k approaches infinity, 3 over k will approach 0 since it's 3 over a very huge number. This makes the whole limit equal to 0. In this case, we will have 0 times the absolute value of x, which means our radius of convergence is equal to 0. And when the radius of convergence is equal to 0, the interval of convergence is equal to negative infinity to infinity. This means that x is convergent for all values across the interval. In the next example, we have the series of negative 3 to the n times x to the north over the square root of n plus 1. We apply the ratio test, so limit as n approaches infinity, then absolute value brackets. Then we sub n plus 1 for every n value in the series. Then we multiply it by the reciprocal of the original series. We can see that negative 3 to the n and x to the n cancel. So we are left with limit as n approaches infinity for 3 times the square root of n plus 1 over the square root of n plus 2 times the absolute value of x. We divided the top and bottom by north inside the square root and get 3 times the square root of 1 over the square root of 1, which is just equal to 3 times the absolute value of x. Now set 3 times the absolute value of x less than 1 and divide both sides by 3, which gives us that the absolute value of x is less than 1 over 3, and 1 over 3 is our radius of convergence. Now our interval of convergence will be x is greater than negative 1 over 3 and less than 1 over 3. We just have to check the endpoints. So when x is equal to negative 1 over 3, the series becomes negative 3 to the power of n times negative 1 over 3 to the power of n over the square root of n plus 1. And using exponent laws, we know that since the numerator has two variables that have the same exponent, we can multiply negative 3 and negative 1 over 3, which leaves us with just 1 to the n, which no matter what n value is plugged in, it will always be 1. So our series become 1 over the square root of n plus 1, now the Bn of. This series is 1 over the square root of n, which is equal to 1 over n to the power of half. And using the p-series test, we know that if p is equal to or less than 1, then the series is divergent. Since 1 over 2 is less than 1, then it's divergent, which means the series is divergent at x is equal to negative 1 over 3. Now let's check the other endpoint. When x is equal to 1 over 3, the series becomes negative 3 to the power of n times 1 over 3 to the n over the square root of n plus 1. We simplify, and we are left with the series of negative 1 to the n over the square root of n plus 1. We see that we can use the alternating series test for this series since it has the negative 1 to the n in the numerator. For it to be convergent using the alternating series test, two conditions must be met. The first one is we have to check that the limit as n approaches infinity is equal to 0. So the limit as n approaches infinity for over the square root of n plus 1, which is Bn, is indeed 0. So the first condition is met. Now the second condition is that Bn must be decreasing. So Bn plus has to be less than Bn. Bn plus 1 is 1 over the square root of n plus 2, which is indeed less than 1 over the square root of n plus 1 since the denominator is greater. And as the denominator gets greater in a rational expression, the smaller it is. This means that the series is convergent at 1 over 3. Therefore, the radius of convergence is 1 over 3, and the interval of convergence is x is greater than negative 1 over 3 and less than or equal to 1 over 3. And you can also write it as negative 1 over 3 to 1 over 3, and make sure to use square brackets for 1 over 3 since that endpoint is included.